Okay, so last time we have discussed, started discussing quantum statistics, and we have seen that because of the indistinguishability of particles, we have to count the states in a different manner. Okay, so in particular. We can, when we have a quantum system, we will have energy levels, and if we want to construct a wave function with a certain number of particles in each single particle energy level, there is only one way to do that. So a collection of occupation numbers for the different single particle energy level will correspond to just one state. Okay, whereas in classical mechanics, if particles are distinguishable, this corresponds to many states. Okay, so what I want to do today is to derive statistical mechanics in this case, and so we are first going to look at the microcanonical ensemble. And so the problem in the microcanonical ensemble is to compute the number of possible microstates, right? So now we consider a system where there is a spectrum of energy levels, and in particular, if the system is very, very large, is microscopical, then there will be a certain for a single particles there will be a certain spectrum of energy levels. And I will consider, and these energy levels will be very, very dense. So what I will do is to consider cells in a very small interval of energy. So this cell will have an energy epsilon E. In the cell, the ith cell, there will be an energy epsilon I, and there will be a number of energy levels, which is Gi. So this Gi is the number of levels in cell I. Okay, and I'm going to first discuss the case where this number is large. Okay, and if you're looking at a very large system, we know that the density of energy level will roughly be proportional to the spacing between energy level will roughly be proportional to 1 over the volume, so that this in a small interval of energy, there will be many energy levels. Okay. Okay. So then, what is the problem? So the problem is that I have to now occupy these energy levels with or these cells with the particles, and so the number of particles which will be in the cell I will be denoted by Ni, this number of particles and so and this number of particles Ni in the microcanonical ensemble has to satisfy the condition that if I sum over all the cells, Ni should be equal to the total number of particles. And if I compute the total energy, then this should be equal to the total energy of the system. So these are two constraints which I have on my system. So what I have to do is consider all the distribution of particles which are consistent with these two equations. Okay, and then the number of ways in which we can see the number of different microstates which correspond to a certain distribution of energy levels. In this case, will simply be the product of all the over all the cells of some let me call it U, which only depend on Ni. Okay, because each cell will be occupied independently. I can okay. So now the problem is what will this number be? So in order to compute this number here, I have to understand in how many ways I can put Ni particles into Gi energy levels. Okay. So in spite of the fact that here I'm grouping energy levels with a very similar energy, but still these energy levels are different in particular. Okay. So and the way in which I can do this will differ in the according to whether I'm considering a classical system of Maxwell-Boltzmann statistics or quantum systems, either with the Bose-Einstein statistics or with the Fermi-Dirac. Okay. So let us compute it for three different cases. So in the case of the Maxwell-Boltzmann statistics, this you have to think in the Maxwell-Boltzmann statistics. You have to think the problem where you have Gi boxes, and you have to put Ni particles in these boxes. Okay, and you have to compute in how many ways you can do this. Okay, and so the number of ways is so for each particle I can choose a box in Ni possible ways. Okay. Sorry. For each particle I can choose a box in Gi possible ways. So I have a factor which is for the Maxwell-Boltzmann case, I have a factor which is equal to Gi to the Ni. Okay. In addition, in the Maxwell-Boltzmann case, you remember that in the Maxwell-Boltzmann case, I will have an overall factor which is equal to the number of ways in which I can distribute these n particles in this group of energy levels. So in the Maxwell-Boltzmann case, the W of Ni actually will not be equal to this, but it will be equal to so it will be equal to n factorial product of I over ni factorial. This is the number of possible ways in which I can distribute the total n particles into the cells. Then I will have this factor gi to the ni, which is the number of ways in which I can distribute ni, small ni particles in gi energy levels. And then since I know that this is wrong because it gives the Gibbs paradox, I will put 1 over n factorial. Okay? So this is the way in which you compute the statistical weight for Maxwell-Boltzmann distribution. So you see that because of this, this number here will be equal to ni gi to the ni divided by ni factorial. Now, in the Fermi-Dirac case, instead, the situation is the following, that the particles are indistinguishable, so that so there is no multinomial factor, but I can put at most 1 particle in each state. Each state can have either 0 or 1 particle because of the Pauli exclusion principle. So that in order to compute in how many ways I can put ni particles, so in particular ni for the Fermi-Dirac case will be less or equal to gi. In order to compute the number of ways in which I can do this in the Fermi-Dirac case, I have to choose, I have to look at the number of possible ways in which I can choose the ni energy levels which are occupied out of the gi energy levels. Okay? And this is just the combinatorial factor. Gi choose ni. Okay? So in the Bose-Einstein case, and of course I will have ni, which is less or equal to gi. So in the Bose-Einstein case, instead I have to consider all the possible ways in which I can distribute these particles. And we have already done this calculation, if you remember, because in the Bose-Einstein case, any distribution of this type will be a possible microstate of my system. And you can see that this is equivalent to the number of configuration between sticks and balls, where, say, if you remove this wall and this wall here, then every configuration, configuration of balls in these boxes, which differ from the number of balls in each boxes, can be represented as a sequence of balls and sticks, where there are ni balls and gi minus 1 sticks. Okay. And so, in how many ways, how many distinct configurations of these ni plus gi minus 1 object can I have? This is again the combinatorial factor. Ni plus gi minus 1, choose ni. Okay? Okay, so now given this, we can compute the entropy. So the entropy S divided by K will be equal to the log of the total number of ways, all the possible ways in which I can put the balls into these particles into this state. So it will be the sum over all the Ni, which are consistent with these two constraints. This prime means that this sum will only run on configurations of sequences of occupation numbers which satisfy these two constraints, of the W of, well, if you want, product over I over all the cells of this U of Ni. Now this is a very, so once you compute this thing, you can compute the thermodynamic. Now this is a very complicated calculation, in particular because I have first to do this sum, and then and this sum is very complicated because of these two constraints, and then I have to take the log. Now, what we can do is to approximate this sum with the largest term. Okay, and so this is an approximation. So, but it is an approximation which we have seen it works also for other systems, because in other cases was very, very appropriate, in particular because this number here will be very, very large. Okay, and okay, so what I want to do today is to first derive the entropy by assuming that we can approximate this sum by the largest possible term. And then we are going to show in a different way that this approximation is really correct. Okay, so the approximation I'm going to take is that this is essentially equal to the log of the product over I of U and I star. So this is where Ni star is what is the solution of the maximum of W and I. So this sequence of this sequence is what maximizes. You can write it also this way. Is what is the argument that maximizes this W. Okay. Under these two constraints here. Okay. Now, of course, this is what maximizes W is also what maximizes the log of W. And in order to deal with these two constraints, what I have to do is to introduce Lagrange multiplier, right? So the Ni star will be a solution of I have to consider the function which is log of W of Ni minus alpha sum over I times Ni minus beta sum over I Ni epsilon I. And I have to look for maxima over the Ni of this function, and then adjust alpha and beta such that these two constraints are satisfied. Okay. Okay, this is clearly equal to the sum over I of this log of U of I minus alpha and I minus. So that now if I take the partial derivative of this with respect to Ni of this thing, then I get d U I d Ni minus alpha beta epsilon I is equal to 0. So this is the equation which I have to satisfy. Okay. Now, in order to solve this equation, I will have to compute this derivative. So what I will do is to use the Stirling approximation for the factorial, because in all the cases this U, in all the cases I wrote before, this U is essentially given by combinatorial factors of numbers which are in any case very, very large. Okay? So,
Can you explain why the WNI changed to
okay, because what I wrote before is that this W, so this is W of Ni, right? W of Ni is the product over all the cell of the number of ways in which you can put the particles in the cell, right? So the log of and here I'm taking just one term. So the log of the product is the sum of the log of the product is the sum of the logs, right? So this thing becomes this, right? And the derivative is yes, there is 1 over ui. Thanks. U over, yeah. Thanks. Okay, so let's do this calculation. So in the so U over I is say in the Maxwell-Boltzmann case is this. So the log of U of Ni is Ni times log Gi, and here I'm taking the Stirling approximation for the factorial. So this is minus Ni log Ni plus Ni. So I can recast this by putting together these two terms. Okay, so I will write this as Ni times log of Gi divided by Ni minus 1 plus 1. Okay, so this is the Maxwell-Boltzmann case. in the Fermi-Dirac case, the U of Ni is Gi over Ni. So the log of U of Ni is equal to Gi log Gi log Gi minus Ni log Ni minus Gi log Ni minus Gi. So what I can do here is to put together the terms which are proportional to Ni, and there is a log of yeah. Is a minus Ni log 1 minus Gi over Ni. And then there is a term proportional to Gi, which is again Gi log of Ni over Gi minus yes, it's Gi minus, sorry. That's why I was getting lost. Thanks. So this is Ni log Gi, Ni, right? Minus Gi, this is okay? No? Okay, so you say there is minus Gi, then there is a plus Ni, they cancel, right? So minus plus Gi minus Ni, right? So this cancel, okay? Okay, so but what you have here is okay now. So the term proportional to Ni is Ni times the log of Gi over Ni minus 1. And then there is minus Gi times the log of 1 minus Ni over Gi. Yes. Okay, so now, so this is the, let me write it here, Ni log Gi over Ni minus 1 minus Gi log. Now, you can do the last case of Boltzmann, Bose-Einstein statistics. Let me write it here. For Bose-Einstein statistics, well, the U of Ni is gi plus ni minus 1, choose ni. And you can find that the log of u of ni is equal to the ni times the log, sorry. So this is what you can find is that well, what you can find is that there is a formula which tells you that you will find the same expression as this, but with this plus, minus turns into a plus, and this all the minus turned into plus signs. Okay, so you can write a formula which encodes the whole three of these cases, where essentially the log of ui is given by ni, the log of di over ni plus a, plus gi over a times the log of 1 plus a and I over gi, where with a equal to 1 you get Bose-Einstein statistics, a equal to minus 1 you get Fermi-Dirac statistics, and a going to 0 you get Maxwell-Boltzmann statistics. So you see a equal to minus 1 clearly gives you this. A which goes to 0, and when a goes to 0 you get a term which is equal to ni gi over ni from here, and the limit when a goes to 0, you can approximate the log of this as a times ni over gi, which times gi divided by ni just gives you ni. So you get the 1. And if you do the calculation, you get that if you take this for Boltzmann, Bose-Einstein statistics, and you use Stirling approximation, then you will get the result there with the plus sign. Okay? Very good. So now what we have to do is to take the derivative of this, with respect to ni of all these minus alpha minus beta times epsilon I, and set it equal to 0. Okay, so this gives us the log of gi over ni plus a, and then there is a derivative down here which gives me plus ni gi over ni plus a, and then the derivative of the argument, which is minus gi over ni squared. And then there is another derivative here, right? So q plus gi over a 1 plus a n I over gi times a over gi, right? The derivative of the argument. So this is the derivative of the first term, and then there is minus alpha minus beta epsilon I is equal to 0. Now, this term and this term cancel, as you can check, because yes, you multiply by yes, you can check that they cancel exactly. And so what you get as a result of this is that the result is that this is equal to alpha plus beta epsilon I, so gi over ni plus, so this is a, plus a is equal to e to the alpha plus epsilon I. So the final result is that the ni star, let me write it here, ni star is equal to gi divided by e to the alpha plus beta epsilon I minus a. Okay, so this is the occupation number of this cell I. Of course, the number of particles is proportional to gi. So the number of particles per energy level is ni star divided by gi, is 1 over this factor here. So you see, when A is equal to 0, when A is equal to 0, this is precisely the Boltzmann factor, okay, e to the minus beta epsilon. You have to remember that alpha and beta have to be fixed in order to satisfy the two constraints. So, and so when whereas when A is equal to 1 or to minus 1, you get the result for the Fermi-Dirac and Bose-Einstein statistics. Okay, so what is how do we get the physics out of this, the thermodynamics out of this? We have to compute now we have to compute our approximation for the entropy, which I remind you is given by S over K was given by the log of the most probable, was our approximation, so that the entropy was given by the logarithm of the most probable distribution of particles consistent with the constraints. And if you compute these, now if you compute this object here on ni star, what you get is that this is ni star, and so the log of gi over ni plus a is just alpha plus beta epsilon. This is alpha plus beta epsilon I. And then here you have plus gi over a times the log of 1 plus a times ni over gi is equal to this, is equal to e to the alpha plus beta epsilon I minus a. So you see, now if you take the sum over I of this first term gives you the total number of particles. Sum over I of ni star gives you alpha times the total number of particles. This gives you beta times the total energy. So here you get alpha times n plus beta times the energy. And then there is the sum over I of this last term. So this last term, you can say take the common, simplify this a little bit. You get minus 1 over A sum over I gi times the log of 1 minus e to the 1 minus A e to the minus alpha minus beta epsilon. Okay? So this is our final result for the entropy in the microcanonical ensemble. And so now you want to give a physical meaning to these parameters alpha and beta. And the way to do this is to remember that the derivative of the entropy with respect to the number of particles, if you keep the energy and the volume fixed, then this is minus the chemical potential divided by temperature, right? And so if you do this derivative here, then the number of particles enters here, so this is just equal to alpha. Is equal to alpha divided by alpha times k. Okay? So this tells you that alpha is minus mu divided by kT. Okay, it's the chemical potential. It's related to the chemical potential. And the other thing is that you know that dS by dE at constant n and d is equal 1 over t. And so this is equal to clearly k times beta. So this tells you that beta is equal to 1 over kT. Okay? And by the way, if you do this, you see again that this combination here, so this combination is precisely something we have already encountered, because it's S divided by K plus mu n over Kt minus E over Kt. So if I take this on the other side, this is exactly equal to PV divided by Kt. And this is equal to minus 1 over A sum over I of Gi log 1 minus this is beta mu minus beta epsilon. Okay, so this is with this formula, essentially you can derive, you have an expression for the pressure as a function of this effectively an equation for the pressure is a function of the energy, number of particles, and volume, where the beta and mu should be a function of considered as a function of number of particles, energy, and volume, which come from inverting these equations. Okay. Now, the other thing you can see from this expression is that if you take the limit when a goes to 0, then if you take limit a goes to 0, then this is, you get minus 1 over a here, sum over I of gi, and then you can approximate this by the first term, which is minus a e to the beta mu minus beta epsilon I. And you see that this is just the sum over I. And then this is precisely the number of particles when AI is equal to 0. And so this is exactly equal to n. So in the case a equal to 0, which is the classical limit, you recover again the ideal gas law. PV is equal to nkt. Okay, so this is consistent. Okay, now this derivation is a bit complicated, partly because we have approximated the entropy by just taking the most probable term. And then because effectively what enters into this calculation are not the variables on which the entropy depends, which is the number of particles, the energy, and the volume, but rather these other variables seem to be more natural variables. Okay. So indeed, the calculation of the thermodynamics for ideal gases is much simpler in the canonical ensemble and in the grand canonical ensemble. Okay, so so I want to show this, and I want to show that in particular one recovers exactly the same result, and it shows that actually the entropy is dominated by the most probable occupation numbers. Okay, so let's discuss the canonical and the grand canonical ensemble. So in this case, what I'm going to do is to do the same calculation, but taking essentially every energy level as a different cell. Okay, so I'm going to do exactly the same calculation. I mean the same calculation as before, but when cells are just composed of one energy level. Okay, then and then each cell then will be specified by the energy of that level. Okay, so instead of the index I, I'm going to use directly the energy of the single particle energy level as an index. Okay, so I will have a number. So n of epsilon will be the number of particles in the energy level, in the level with energy E. And I'm considering non-degenerate levels at this point. Okay, so I'm considering particles. So this would essentially correspond to, for example, ideal gas of spinless particles. Okay. So the number of particles for each level can either be it can be 0, 1, 2, it can be a positive number for Maxwell-Boltzmann statistics and Bose-Einstein statistics. It can be only 0 or 1 for the Fermi-Dirac statistics. Okay. And so, for example, and then my microstate will be essentially given by all possible ways in which I can occupy the single particle energy levels, which are consistent in the canonical ensemble with the total number of particles being fixed. Okay? So in the canonical ensemble, what I have to do is to compute the partition function. So the partition function will be exactly the sum over all these occupation numbers of e to the minus beta times the energy, and the energy will just be the sum over all energy levels of n epsilon times the energy of that level. Okay. Now, if I so this is the calculation I have to do for quantum statistics. So if I want to do, if I want to compute this in the case of classical statistics, I should also remember the fact that a particular set of occupation numbers gives me, contributes, I should put a 1 over n epsilon factorial here because of the counting, because each set of occupation numbers do not correspond to just one state, okay, in classical statistics. But let's confine our discussion to quantum statistics, okay, for the moment. Okay, so you see, now this problem is still a bit complicated because I have to do this sum with this constraint. So it is much more practical to use the grand canonical ensemble. In the grand canonical ensemble, I have to compute the grand partition function, which is the sum of a number of particles which goes from 0 to infinity, fugacity to the n times partition function, of a system of n particles. Okay. Now this is if I just rewrite it, so I have 0 to infinity, and then sum over all the number of particles consistent with that constraint. Now this n here, I can just write it in this form here. So that I have z e to the minus beta times the energy to the power n epsilon product over all the states. Okay? And now you see that, well, this is, what I have to do is to sum this object first over all the states with the constraint that they have a fixed sum, and then I have to sum over the sum. So that essentially this is equivalent to summing this object here over all the possible occupation numbers without any constraint. Okay? Because then I'm summing over all the values of n. So, and then this is just the sum over all the possible n of epsilon of this product of epsilon z e to the minus beta epsilon to the n epsilon. And now you see this is like a multiple integral of a function which is just factorized. So I can factorize the sum. Okay? So I can write this as the product over all the energy levels of a sum over the single energy level, but depending on the statistics, of z e to the minus beta epsilon to the n epsilon. Okay? So this is a very, it's much simpler. Okay? So in particular, if I have in the Bose-Einstein statistics, this is just the product of epsilon. So this Bose-Einstein statistics, this sum over n epsilon goes from over all the positive integers, including 0, and non-negative integers. So this is just a geometric series. So this is a sum over epsilon of 1 over 1 minus z e to the minus beta epsilon. Okay, for the Bose-Einstein statistics. Whereas in the case of the Fermi-Dirac statistics, this is just the first two terms. I have to consider just the first two terms. So this is 1 plus z e to the minus beta epsilon. So this is z. So this is the Fermi-Dirac statistics. So you see that effectively you can write the log of z the log of z, you can write it again in this form here. You can combine these two results in a form which is this one. So of course, if I take the log, the product becomes a sum, and then I have sum over epsilon of I can write this 1 over a times the log of 1 minus a z e to the minus beta epsilon. Okay? So you see, if I take a equal to 1, I have Bose-Einstein statistics. If I take a equal to minus 1, instead I will get the log of this. Okay? And you can check that, so we know that the log of the grand canonical partition function is equal to PV over KT, right? And this is exactly the formula that we have derived previously with z equal to e to the beta mu. Okay? So it's exactly the same formula. So from here you can derive all the thermodynamics But you see the derivation of the thermodynamics in the grand canonical ensemble is much simpler. So it's much. Okay, and by the way, I mean, you can also see that, well, the limit when A goes to 0 reproduces also the classical limit here. So, now, so the other thing which you see from this is that now you can compute what is the mean occupation number. So how many particles will you find in a state of energy epsilon, single particle energy level? And the way to compute this is essentially that, well, what you should do is to sum over all the, in the grand canonical ensemble, over all the possible state. So let me call this n of a particular state epsilon bar. Okay. You should sum over all the possible occupation numbers of the statistical weight, which is z e to the minus beta epsilon to the n epsilon times n epsilon bar, and then divide this by sum over all the possible occupation numbers z e to the minus beta epsilon to the n epsilon. Right? So this is what you have to do. Now all these you see all these sums here essentially factorize, so that what you can read from here is that, well, this essentially should be the sum over all the n from 0 to infinity, the probability that n epsilon is equal to n times n, right? So this is just the expected value of this thing. So this probability here is exactly equal to this object here. Okay, so the probability that n epsilon is equal to n is will be exactly proportional to this factor here, z e to the minus beta epsilon to the n times a normalization factor. Okay? Okay? And from this, you can compute, well, what is this normalization factor? So, well, in the case of Bose-Einstein statistics, you have to normalize from n, which goes from 0 to infinity. When it's here, so this factor a will be just 1 minus z e to the minus beta epsilon bar times z e to the minus beta to the n. And in the case, this is for the Bose-Einstein statistics. In the case of Fermi-Dirac, you have just to sum over n equal to 0 and n equal to 1. Okay, so this will be z e to the minus beta epsilon bar to the n divided by 1 plus z e to the minus beta times epsilon bar. Okay, this is for the Fermi-Dirac. Now, now it is very easy to compute the expected number of particles in the energy level epsilon bar, and this will be given by well, it will be essentially 1 divided by e to the beta, well, z to the minus 1 e to the beta epsilon bar minus a. Well, this a again is equal to 1 for the Bose-Einstein statistics and minus 1 for the Fermi-Dirac. Okay. So in order to compute it in this case, you just have to multiply by n and sum over n, this, right? So, and you use the usual trick that you can write. So if the probability of n is proportional, is a geometric probability, so if p of n is equal 1 minus x times x to the n, then you can compute n average as x times d over dx of the sum x times 1 minus x, the sum n equal to 0 of the derivative with respect to x of sum over n from 0 to infinity x to the n, right? Because when you take this derivative, this gives you n times x to the n minus 1. With an x, you get, again, n times x to the n, then 1 minus x. So this is exactly what you should get. And then this is x, 1 minus x, times the derivative of this is 1 over 1 over x. So this is 1 over 1 minus x squared. Okay? So this is x divided by 1 minus x. This is 1 over x minus 1. Okay? And with x, which is equal to z e to the minus beta epsilon, you get exactly this. Okay? So this is the usual trick that we have used already several times. Very good. So now we can discuss what are quantum effects. And by the way, let me just mention that in the Maxwell-Boltzmann case, so you see the probability of n of epsilon is geometric for the Bose-Einstein distribution. Is instead, well, only 0, 1, compared to 0, 1 on Fermi-Dirac. For the Maxwell-Boltzmann case, you can do the whole derivation. The only thing which changes is that there is a factor 1 over n factorial on each of the energy level. So for the Maxwell-Boltzmann distribution, you can see that the probability that a particular energy level is occupied with n particles will be the same result which we have found previously, but with divided by n factorial. And the normalization in this case is just e to the minus zeta, e to the minus beta epsilon. So this is the Poisson distribution. So the distribution of occupation numbers in the classical case is given by a Poisson distribution, whereas in the other cases it is given by geometric distribution. Notice that say the Poisson distribution is a distribution for which the variance is equal to the mean. So the relative fluctuation, which is the standard deviation divided by the mean, will be proportional to 1 over square root of the average of the expected value. Okay. Whereas here the standard deviation, if you compute what is the fluctuation, so n epsilon squared minus n epsilon squared. So this is the variance divided by n epsilon squared. What you can find is that this is 1 over n epsilon plus a. Okay, so when the classical case again is when a is equal to 0, and this tells you that the variance is equal to the expected value. When in the case of the Bose statistics, the fluctuations are larger. Fluctuations are larger than with respect to the classical case. And the Fermi case, the fluctuations of the number of particles is smaller. Okay, because there are only 2 possible states which are allowed. And indeed, so in the Fermi-Dirac case, you see that the variance is just equal to the average number of particles times 1 minus the average number of particles. So which is what you get for a variable which can be either 0 or 1. Now, the other thing which you see from this formula is that the quantum effect will become important when the occupation number is large. When you have a system where the occupation number is large, and whereas when all the energy levels have a very low occupation numbers, then this term will be much larger than 1. Okay, and then the presence, this term will be essentially negligible. Okay, so when is it that these occupation numbers are very small? Well, you see. Typically, this is an object which depends on the variable beta epsilon minus mu. Okay, so it depends on only this combination of variable beta epsilon minus mu. And the way in which it depends on this is the following. So if you write the average occupation number of energy epsilon, then imagine that this is 0. Then, so for the Fermi-Dirac case, you see that when this argument becomes very negative, and a is equal to -1, then this becomes negligible with respect to this. So in the Fermi-Dirac case, you converge to a constant. The occupation will converge to a constant, and in particular, it will converge to 1. In the instead, in the Maxwell, in the Bose-Einstein statistics, you see that there is a divergence when beta epsilon minus mu is equal to 0. Okay, so there is a so the Bose-Einstein statistics will have a divergence here, whereas the Maxwell-Boltzmann statistics, where A is equal to 0, is just an exponential. Okay, is Maxwell-Boltzmann. So you see that the classical the classical limit is when really takes place when when you are far to the right in this plot. So when the chemical potential is large and negative with respect to the typical energy of single energy levels. Okay. Whereas if you are in the regime of small chemical potential, or say large chemical potential, then the quantum effects become very important. And again, you can see that these conditions are essentially the same that we have discussed last time. That essentially the chemical potential will be large and negative when either you are at a low density or at high temperatures. Okay. Okay, so very good. So now what we can do is to derive some thermodynamics from this, and so let us consider ideal gases. So for an ideal gas which is monatomic and without spin, so the energy actually is a function of momentum. And typically, say, if you consider non-relativistic gases, then this will be equal to this. And you can substitute sum over the energies as with integrals over momentum. And actually, if everything depends only on the absolute value of the momentum, you can write this in this form. There is 4 pi times v. I mean, this is the same calculation we have done, counting the states of a classical system. Consider that you have plane waves, and that plane waves in a finite box. You have boundary conditions, and so the wave number can also only be 2 pi n divided by L, etc., etc. Okay. So if you do this, then you can write the grand canonical partition, grand canonical potential as minus 1 over A. This A again will be equal to the 1 for Bose, minus 1 for Fermi, and 0 for classical case. And well, generally you have the sum over epsilon of log 1 minus a z e to the minus beta times epsilon. Now you can turn this into an equation for an integral over momentum. And so this is minus 4 pi v over a h cube times the integral from 0 to infinity p squared dp of the log of 1 minus a z e to the minus beta epsilon of p. Very good. So it is useful now to do a little bit of manipulation of this to do an integral by parts. So I'm going to integrate this and differentiate this. So if you do this, this is minus 4 pi v over a h cube. And then the finite term is p3 over 3 times the log of this thing. And then there is the other term, which is minus, well, this is computed in 0 and infinity, where the momentum is equal to 0 or infinity. And it's minus the integral from 0 to infinity of dp of p3 divided by 3. So this is pressure, okay? So this is a big P and this is small p, okay? So. And then I have to put the derivative of this. The derivative of this is again 1 over z to the minus 1 e to the beta epsilon minus a, and then actually it should be a to the minus 1. Okay, and then there is a derivative, there is a beta times the derivative of the energy with respect to the momentum. Okay. Right, so this term is equal to 0 because in infinity this log has the energy with infinite momentum, which is infinity, so this is 0. And so the log of 1 is equal to 0, so this term is 0. And it's going to 0 much faster than p cube. And for momentum equal to 0, this is 0. Okay, so this is equal to 0, and here so and here you have so you can write this as as 4 pi beta times v divided by 3 h cube integral from 0 to infinity dp p3 d epsilon dp divided by e to the z to the minus 1 now I mean there is this factor a which you have to check in the calculation, but if you do the calculation correctly, this is what you get. Okay, so this is an interesting formula because it tells you that the pressure is equal to 4 pi v divided by 3h cube times the integral from 0 to infinity in dp p squared of z to the minus 1 e to the beta epsilon minus a times p times d epsilon dp. Now, if you, the meaning of this equation is clear if you compute the number of particles. The number of particles will be equal to the sum over all the energy level of n epsilon, right? And if you do again the change of variables in this manner, you find that this is 4 pi v over h cube times the integral dp of p squared, and here you have 1 over the average number of particles in energy level epsilon, which is z to the minus 1 e to the beta epsilon minus a. So you see that if you sorry, there is no v, of course, here. No, there is a v. Oh, there is no v here, right? So v and v cancel, and beta and kt cancel. Now, you see the density. So the density is equal to this 4 pi h cube integral dp p squared 1 over minus 1 e to the beta epsilon a. So you can see that this you can interpret this object as being related to the average of the momentum times the derivative of the energy of the single particle with respect to the momentum, which is the velocity. So you can rewrite this as pressure being, so because if you divide, you see, you can consider this as an average over the distribution of particles. So from this, here you get a probability distribution on the different energy level if you divide by n. So what you can write is that the pressure is equal to n divided by 3. If you compare these two equations, the pressure is equal to n divided by 3v of essentially the average of this thing, which is n over 3 v times the average of. So if this is the Hamiltonian of the single particle, this is q dot, right? P times single particle velocity. So this is an interesting relation because it's a relation which holds for all the gases, both classical and quantum, Fermi and Dirac. And in particular, so if, for example, if you have an energy, if the energy, so if the energy is of this form, you know, is proportional to momentum to some power s, then you see that P times d epsilon dp is essentially, then if this is true, then P times d epsilon dp is equal to S times the average energy, right? And then this equation becomes that P is equal to N times the average energy is essentially the energy divided by S times E divided by 3N. So you see for S equal to 2, this is the classical, so this is the energy for non-relativistic gases, the relation between the pressure and the energy for non-relativistic gases. So you see this relation holds for all classical, for all ideal gases. Okay. And the other interesting point of this relation is that you can also derive this relation from kinetic considerations, okay? Because,
What are the possible values of this? I mean, for instance, S can be 2, right?
Yeah.
Just if we consider kinetic energy.
Yes.
And the
Yeah.
pressure would be like 2/3 of the energy density.
Yes.
Then,
Yes.
then it means we have 1/3, right? Okay, P minus.
Yes.
Then,
So this is the pressure, sorry, it's not the momentum.
okay, yeah,
The pressure is 2/3 of the energy density. Yes.
Yeah, then we are saying, okay, then we have, okay, there is a factor of 1/3 which remains.
Mm-hmm.
So what does really
Okay, where does this factor 1/3 comes? So one way, the other way to derive this relation is really by kinetic considerations. So by the fact, you can think of, so this 3 is essentially the dimension.
Yeah, but the pressure is just 2/3 of the energy per particle, right? And then it means there is something which is 1/3, like 1/3 of the total energy which remains.
The pressure is 2/3 of the energy. Okay, yes, you can say. Okay, so why do you think that the energy per particle should all go into pressure or something?
Yeah, that's my question. Only 2/3 of the energy per particle is just for the pressure,
Mm-hmm.
and 1/3 is then there is 1/3 which is I don't know, for something I don't know.
Okay, so let's see. So one way to see this is what contributes to the pressure, right? So the pressure is given by the fact that these particles hit the wall and they transfer momentum. Okay, so so you can think that the pressure is really how much force acts per unit area. Okay, and now you can say what is the force? The force is given by the derivative of the momentum, right? So when you have a particle which hits and bounces back, so if this is the coordinate x, okay, so the change in the momentum is 2 times px, no, because the particle enters with momentum px and exits with momentum minus px, okay. And these, of course, and now in order to consider, you have to consider how many particles will hit the wall per unit time. Okay, so this is the change in time dt. This is the momentum transfer, the derivative of the momentum, and then you have to multiply this by the number of particles which hit the wall in that time interval, and this will be proportional to the number of particles which are in a small volume close to the wall. Okay, and the size of this thing should be Vx times dt, and then the volume you have to multiply by dA. Okay, so that you see that the pressure from this will be equal to twice Px times Vx. And now you have to essentially take an average, okay, over all the particles. Okay. So now, and essentially this is, you get a factor 1/3 because x is just one of the three coordinates. Okay, so this will be 1/3 of the, so if you consider the absolute value of the momentum times the absolute value of the velocity, so there is a factor 1/3. And so this is where essentially this 1/3 comes from. Now, and and of course you have the density. You have to compute the number of particles per unit volume. Okay, you are also to introduce that. So, so if you change the dimension, then this 3 will become D, and if you change this S, the 2 will become different number.